In this video, we'll look at multiple regression analysis. So I'll show you how to run a specific multiple regression analysis that's very similar to your homework assignment. And we'll discuss regression diagnostics as well. So we're not going to get into the most detailed explanation of regression diagnostics. I'm going to focus on some basics. So let's go ahead and just discuss a couple of these different factors we want to check. One of them is outliers. So when we have a data set, when we're cleaning our data and preparing for analysis, we look for cases that are missing, cases that are entered incorrectly, but we don't always catch everything. We don't catch what are known as outliers. Outliers can be values that are extreme. They can be extreme for different reasons. For instance, if we're measuring height, there could be somebody who's 7'3" or something, some ridiculously tall height, right? Where majority of people are much shorter than that. That doesn't mean that anything's wrong, because some people are just tall, or we could be doing weight or depression or any of these measures, and you can have people who have extremely high or extremely low scores. And that's, if we understand the normal distribution, that's within the limits of normality. They might be extremely far at the ends of our distribution, at the tails of our distribution, but they can occur. Sometimes, though, these extreme cases are just data entry errors. So that's one thing we want to look at. We want to look for extreme cases. Extreme cases can impact our results. It can impact our actual outcome, or the parameter estimates, the betas, the B's in our regression model. So we want to check for those. I'm only going to cover one of these here, since this is just an introductory course. I'm looking at residuals. Residual is the difference between the predicted value and the actual value. Earlier I showed you what the prediction model looks like. Go back a little further. Here, so this was your typical prediction model. You'll notice that the y has a little hat over it. And you'll notice also that we end with in this case we had multiple predictor variables, k predictor variables. And each of these x's has a little I, if you recall. That's because these are individualized values, and so does the prediction. So this is predicting one score on whatever your outcome variable is based on these specific predictors. Now you'll notice that when we move from the prediction model to the model with the actual model to get an individual's actual score. So this is the score they'd have on your outcome variable. You're always going to have scores on the individual's predictors and outcome variables. You're just trying to find the best model to enhance the predictability. You'll notice that there is no hat over the y. Maybe it was windy and it's lost its hat, but there's an error term. So the error is we call this residual. That's the difference between the predicted value and the observed outcome value. So this is your error term, and our error term is individualized. These errors are distributed across all the participants in your sample, across the population, in a standard normal form. We can judge whether or not someone is an outlier by looking at how far they are from the mean of 0 in these residuals. We call them standardized residuals. Standardized with mean of 0 and standard deviation of 1. We consider a residual problematic. I mean, that's dependent on the researcher, but we like to consider one that's 3 standard deviations above the mean, above or below the mean, to be problematic. As we know from this, I mean, there's 2 different rules. One is the Chebyshev's, but we tend to use I think it's called the empirical rule, where we look at what proportion of the values in a standard normal distribution are within plus or minus 3 standard deviations of the mean. We know it's 99.7%, so it's like 0.3% or outside of plus or minus 3 standard deviations of the mean. So these are very unlikely to occur, so we can consider those problematic. That doesn't mean that we should do anything specific with them. We have to take a look at how they impact the model. If they don't really impact the model in a negative way, we don't want to eliminate them. One reason you don't want to always automatically eliminate outliers is because data collection is a very difficult and expensive process, and people apply for grants and get large amounts of funding to do this, and every single participant is critical. So we don't want to just throw people out because we don't like the way their data look. So we have to do a full investigation. But if you have a value with a residual that's plus or minus 3 standard deviations, or 3 standard deviations from the mean, that's a matter of negative or positive, that's something that just to look at, to be concerned about perhaps. We also check for multicollinearity. Multicollinearity is the shared variation among different variables in predictor variables. So ideally or correlation among the predictor variables. Ideally we don't want the predictor variables to be correlated. Ideally we'd like them to be completely uncorrelated, so each one would capture a certain percentage of the variation in our predicted or variable, right, in our outcome variable. Because that's what we're doing. We're trying to understand, in making a prediction, we want to explain what we see, the variability we see in our outcome variable. And that's why we're proposing these models. By the way, in case you don't know, and I know I mentioned this in class, the best predictor of a variable in the absence of any other information is its mean. So we certainly want to do a better job than just taking the mean of our outcome variable. There are 2 measures we'll look at, although you'll see in SPSS there's more information, but I'm going to skip over that because that's beyond the scope of this lecture, beyond the scope of this course. But the ones that I like are tolerance and variance inflation factor. So tolerance is the proportion of the variance of a predictor that is accounted for by the other predictor variable. So it's like you're doing a little regression with each of the predictors being the outcome and the other predictors being the predictors. That's kind of redundant. Larger values of tolerance are better. So we don't want to have other variables accounting for a great deal of variation in the one predictor of interest. And then there's the variance inflation factor, which is 1 divided by the tolerance. They're just two different perspectives on the same issue. Heuristics, tolerance values less than 0.1 are troubling. Well, yeah, because you're not the other variables are accounting for a greater deal of the variation in the outcome, and VIF values greater than 10 are worrying. We also check for homoscedasticity. Ideally, we want the variance of the residuals to be constant across different values of the predictor. So each predictor has multiple values. Like if one of our predictors is sex, we could have male and female. We don't want to see different variability in our residuals, right? The residual, we just talked about the difference between the predicted and the actual value. We don't want to see different spread for males and females. They should be equal. So otherwise, the model will be better predictor for one sex than it is for the other. So we don't want that. We can plot this using the standardized residuals. I usually in a table or in a figure. I'll let the y-axis be the z residual, and the x value be the standardized predictor value. Finally, one more thing we want to look at is the coefficient of determination. That's the total amount of variation in the outcome variable, outcome variable attributable to the predictor variables. And we also look at something called R-squared change. So we'll see the coefficient of determination is also known as R-squared. And the R-squared change, we'll use that when we enter our primary variable of interest into the model after we enter the control variables first. So let's try one. So does support for physical activity predict physical activity enjoyment? Let's conduct this in 2 steps. In the first step, we'll enter the control variables, biological sex, parental education. This makes sense to me because now it's interesting to point out here that regression analysis should be done based on your knowledge. I don't recommend using these backwards and forward methods where everything is done for you mathematically through your software. I recommend that you know what you're doing first and enter the model. We call forced entry. Enter the model on your own, the way you believe it should be, because that's what science is about. It's about you testing hypotheses, and you should know what you're doing. So we want to control, and the reason I'm controlling for these, because there may be sex differences in physical activity enjoyment. Parental education is probably something that'll impact it. Hours of moderate, vigorous physical activity. Certainly more physically active you are, probably enjoy it a lot, so that should be controlled for. Neighborhood characteristics, including neighborhood crime, how much traffic there is, and walkability. These are all good all good control variables. In the second step, I'm entering physical activity support. So I want to know if physical activity support predicts enjoyment, right? So I have to control for these variables first, and I want to see if it above and beyond that does have an impact. All right, let's go ahead and we'll do this two different ways. I guess I should, well, I'll start with syntax because I prefer syntax. Anybody who knows me, you know that the reason we do syntax is because when we have these large data sets, it's a lot easier to use syntax than it is to use the drop-down tab. So I'll do that. So here we will run our syntax. I ask for coefficients. The outs is like where we look at variables that are not in the model yet until they tell us whether or not we should include them. We get just an Anova Table, collinearity diagnostics, R-square change, and all this really good stuff here. I don't really need the in and out because we're not using one of these canned methods, but it's okay to have this in there. So the canned methods are the backwards and forward entry. Let's see, anything else here that's so the reason I'm discussing this as I do is one way to learn syntax is to run the analysis in the drop-down tab just to get the syntax, and then you copy and paste the syntax into a syntax file. And that's what I did here. This is your cheating way to learn syntax. It's awesome. But you got to know what you're doing, of course. Then I put in my dependent variable, which is physical activity enjoyment. This was done at wave 1 of this study. Person's biological sex, parental education, moderate vigorous physical activity, from the physical activity recall. These are all really cool, good measures. And then crime, traffic, and neighborhood safety, and support for physical activity. Ask for a scatter plot of the residuals. And I also ask for outliers and at 3 standard deviations. All right, let's do it. So to run an analysis like this, first of all, just in case you're not familiar or you can't remember, you always have to get your file. When you're running it with syntax, you can use a get file command. This is the same command that would happen if you just double-click the link in your computer to your file. You notice that there's 2 components here. One is the address, that's the address, right? And then there's the file name. .sav is the file name for every file in. That's an SPSS file. If I used a different file format, I'd have to make some adjustments. And so this was, I originally had run a simple regression with just one predictor variable versus multiple regression. To run something, you highlight it. Okay? And you just click the run button. And it'll give me the output. Lots of names here and stuff. That's all great, but I don't really need that right now. But it shows me that there's 2 different models. So it says model 1, so that's just the control variables. Model 2 is entering the next variable, right? All right, so let's see. Let's look at what we have here. This is basically where I'm looking for the R-square change. I want to see how much more of the proportion, how much increase in the proportion of variance accounted for by the inclusion of support to the model. We see the R-square change. The R-square, now there's 2 different R-square. One is the R-square adjusted is better for making generalizations to the population as a whole. So let's look at just regular R-square. So we went from 0.171 to 0.266, and that was an increase of here 0.095. So if we go from 17% increase to a 9.5% increase. This is statistically significant. Of course, it's statistically significant. These are from an Anova table, or from an an F distribution. So you have the degrees of freedom in the numerator and the denominator. But based on these degrees of freedom in the denominator, you can see the sample size is very large. So of course, it'll be significant. By the way, when you have a large sample size, it's very common for you to have statistical significance. Here's your Anova table. This is just your basically telling you if the model is significant, and that if you've studied Anova, you know what this table looks like. I love Anova tables because it's really easy to work them all out. Everything can be worked out through the model. Like for instance, you take sum of square regression divided by the degrees of freedom regression, you get this. You take the mean square for regression divided by the mean square residual, and you get the F value, and it's beautiful, right? I love it. It's a great way to put it. But for most of us, when we're doing regression, we're not that interested in the model itself. We're more interested in the coefficients, whether they're significant or not significant. So we really want to focus on Model 2, because Model 2 is the one that includes the variable of interest, which is our physical activity support. By the way, the order in which you enter the variables is important. In this way, I included 2 steps. So in the first step, I entered the control variables, and then the second step, I entered the variable that I'm interested in. So that kind of gives me some control over ordering. I also ordered everything from with the SES variables first, the most basic demographics, and then physical activity, then the neighborhood characteristics. Ordering can have an impact on your outcomes. So you have to be wary of that when you're running these models, or at least understand that. Let's take a look at our outcome. Where is it here? Okay. We want to know what's statistically significant, first of all. So we have different values. We have the unstandardized B values, and then we have the standardized coefficient betas. So these are used for interpretation. The beauty of the standardized coefficient beta is you can make direct comparisons regardless of the scale of the predictor variable. When you look at the unstandardized, it's really hard to make those comparisons. And we get confidence intervals, and then we get the collinearity statistics, right? Let's start down here. So now this is difficult because these headings are up top. So we have the variance, inflation factors, and tolerance. We wanted the tolerance values to be high, right? And they all look really good. Yeah, they all look really good. The variance inflation factors are less than 10. These are greater than 0.1, so they're all really good. Although, yeah, they all look good. Statistical significance. In SPSS, sig means p-value, right? So we want to look at this. This is your t-test value. That's how you test for significance of your regression coefficients. We look at it one at a time, right? When we interpret one regression coefficient, it's holding all other variables constant. That's something you have to add when you're writing up your results, because when we're dealing with one regression coefficient, all the other variables are held at their mean for every individual, so that they're constant. So here, with a large sample, I like to have a p-value of 0.01, because we have such a large sample. An alpha of 0.01. I mean, you can use the standard alpha of 0.05 if you like, but when you have these large sample sizes, we have a lot of power, the probability of rejecting a false null hypothesis get overpowered. So it's better to actually shrink your alpha a little bit. Like, with that in mind, biological sex remains significant. If we have an alpha of 0.05, we'll see that parental education is not significant. And here parental education is labeled so that you have both parents have a high school education or less. That's the highest value, because generally in public health, having a high school education or less is more predictive of negative health outcomes. But if we use a criteria criterion with an N of 0.05, alpha 0.05, this is significant, but if we use 0.01, it's not significant. So I'd report that as significant 0.05, not significant at 0.01. Of course, physical activity is significantly related. By the way, it's interesting if we look at some of these values, what the coefficients are. Oh, I have to look at what biological sex is. How did I forget that? What is your sex? 0 is male and 1 is female. You know thy variables. 0 is, what did I say was 0 is male and 1 is female? Okay, so when we interpret this, we can see that the effect of sex is negative, so that females have less support for physical activity than males. What a shock. Parents are discriminating against their kids. Of course, physical activity is positive related to support, so if you're already doing it, you get more support. You enjoy it. Neighborhood safety from crime, more likely to be enjoying physical activity. Traffic and places for cycling and walking, not significant. What about support? Well, support is statistically significant here. All right, so that's what we expected. So we controlled for all those variables. We show that physical activity support has a significant effect on physical activity enjoyment. This would be a nice little paper. I should submit this. Let's look at the interpretation. Okay, interpretation is, well, actually, before we do that, let's look at some other stuff. You'll notice that this is where the outs, or whatever I had in the code, manifests. So it says that if we exclude this, the only variable excluded from model 1 is support, and it would be significant if we added it in there. It gives you all the diagnostics as well. So this one I'm going to skip over here, but this is another way to look at regression diagnostics. According to some heuristics, this condition index greater than 15 is an indicator that there could be multicollinearity. And so I think that if there are any problems here, it looks like it would be among these neighborhood variables. These values, if they're 0.9 and above, they're not good, but we don't have any that are that high. But it's worth looking at. There's probably some, it makes sense. They come from the same measure, the ones about neighborhood safety, crime, and safety from traffic, and places to walk, etc. Those are coming from the same measure, so there could be some overlap there. But we looked at the VIF and the tolerance, and we didn't seem to have any issue. This is a look at the residuals. You'll notice that there are several cases. This is the case number where the residuals are higher. So I'm not really sure if it's worth looking at because this is such a large sample size. They're kind of probably noise in this case and have a little effect on the outcomes. But this is how it looks. See the residuals. There they are. They're 3 standard deviations below the mean. They're negative. This just gives you some more look at those residual statistics. This is our plotting. It's a scatter plot because you have individualized points for the output, the outcome variable, and the predictor, standardized predictor variables. If you look at this scatter plot, it's kind of difficult to look. There's a tendency for them to just go to cluster in this nice little tubular shape here, although there's little less cluster here than there is out here. So it's hard to say, is this problematic? It may be, but you have fewer values that are outside of this nice kind of parallel shape going down here. This is something that's worth investigating, but this is an idea of what we're looking for when we're looking for at the standardized residuals. What we'd like to see is a nice not symmetry, but we want to see a nice scattering where we don't see any any funneling shape. So I'd say there's a little bit of a funneling shape here, but again, you have fewer cases out here than you do in this clustering here. So I'm not really sure if this is problematic or not, but I would report it for sure. You always want to report everything when you're reporting your results. All right, so that's how you run this analysis using syntax. If I wanted to run it without syntax, and I want it to be, I call this cheating, but it's not really cheating because sometimes it's actually harder. It may be hard in this case. So let's see. I'm going to try to run this because at least I'll show you how difficult it can be. So this is a drop-down tab. I want to use a linear regression. Okay. The reason I say it's difficult is because what we want to do is we want to drag the variables to where they belong, dependent and independent variables, right? Problem is that I have this long list of variables, and you see how I have to read down all of them? So this is, I don't have a lot of variables in here, but imagine if I had 1,000 variables, and that's very common to have large data sets. First thing, I don't like using the descriptions. I usually know the variable name, so if I right-click within this box and then click variable name, it'll give me the variable name. So we were trying to predict physical activity enjoyment. We put it in the dependent category. And the first step, we wanted to have biological sex. We said, what did we have? Parental education, right? And we had physical activity, moderate and vigorous physical activity. Here it is. I think that's, oh, and then the neighborhood variables. We had crime. Now if I hit the shift key and then hit the last variable in the list, it'll highlight all three of them. And I can drag these suckers over here. All right, so we got it. I think. Okay. I can rearrange the ordering if I want. Let's see, where do I have that? Let's see, I can move it here. Just I want to stay consistent with what I had. I had it after parental education, right? It's not cooperating with me. Here it is. Right here, I think. Almost, one more. There you go. All right, that's what I had in the listing. All right, that was my first step. So now I go to next step, and then the next step I entered support, physical activity support. And I had that here somewhere. Here it is. Okay. I asked for certain statistics, model fit, confidence intervals, 95% R-squared change. You can ask for descriptive statistics, collinearity diagnostics. I think I did residuals, case-wise diagnostic. Yep. Outliers outside of 3 reported those. Hit continue here. So you get all these nice options. Plots, I wanted these residual plots. I wanted the Z residual to be the Y variable and the Z predictor to be the X variable. You can ask for other things too, histograms for the standardized residuals, etc. I'm just showing you what I asked for. You can actually save output to, what other options do I need? Listwise tends to be the method of choice, which is if one value is missing on any of the variables, the whole case is deleted, but you can use other ones. You can replace with the mean. This is an imputation method. I wouldn't recommend that. I will include the constant in the equation. Well, you might want to write down the equation. So there's also bootstrapping if you're worried about your sample size. Okay, let's hit OK and run this. So this is the same analysis we just ran, assuming that I entered all the variables correctly in here. It looks like I did. Yep, looks exactly the same. You get the same output. There you go. So I showed you 2 different ways to run this. I suggest using syntax because syntax translates, not one-to-one, but it translates across programs, and learning syntax is much more valuable to your resume than saying I can use the drop-down tab in SPSS. But either case, you have what you need. Thank you very much. I hope you enjoyed this. Bye.